Okay. As I said during our first meeting, I'm going to start off using the Bride book up there. And I'm going to go through the slides for the first chapter of the Bride book. There's 153 slides in this set of slides, so I'm not going to go through all 153 slides, and I'm going to skip a lot of them. Most of what I'm going to talk about today is historical information. It will not be, 99% of today won't be on the final exam. This is just background material. Just kind of sit back, listen to it, just kind of get a feel for where the industry's come from and the history of microprocessors and how they came about in desktop computers. So, right there. So, there's like, there. Okay, and this book will be made available to you. So, it's a fairly in-depth book, and I'm not going to cover the entire book. As I said, about halfway through the semester, I'm going to switch gears and go to the 8051. But this book does a much better job of going through the background of microprocessors and what they do and where they came from. So, okay. And this is not looking like it's going to be a good hour. If this keeps doing this, then it's going to be a very short session. Unfortunately, back when I first started teaching, we used whiteboards or blackboards, and then we went to the whiteboards, and then we went to the overhead projectors we wrote with on pens, and now everything's done with PowerPoints and computers, which means that we need projectors that work. And right now, this one seems to be going through that. So, we're going to be talking briefly about Intel microprocessors right there. So, both the 8086 that the Bride book talks about for the most part and the 8051 are Intel processors right there. So this particular chapter kind of goes over an overview of the various Intel microprocessors. It doesn't really talk about the microcontrollers at all. With a little history of computers, and then we get into the function of the microprocessor, where we actually start really the course right there. The terms and jargon, we'll talk a little bit about that, because people in the computer world, the microprocessor world, we tend to speak a language other than English, and definitely other than Malay. That there. It's like, that there. My wife, who understands pretty good English, doesn't understand when I talk to somebody about computers up there. So it is, and that there, and actually my oldest son does, but my youngest son doesn't. My youngest son is up there. So again, this is the objectives of the chapter. I'm not going to go through everything in great detail, especially when we talk about protected mode memory systems and some of that stuff up there. In detailed history of the computer and list all the applications performed by computer systems. In an overview of the various 80x86 in the Pentium family, we're not going to get in huge detail on all the various processors. We will look at the block diagram of a computer system and explain the purpose of each block. That will be on the final exam. That there. So part of this, as I said, most of this won't be, but that definitely is part of the course. The function of the microprocessor is basic operation. Again, that will be part of this. That there. We probably won't get to that this hour. I know we're scheduled for 2 hours, but those who've had me in the past know that I'm not good for 2 hours on a good day, and this is not a good day. Right there. So, and define the components of the memory system, we won't talk about that there. We won't review in great detail binary, decimal, and hexadecimal numbers. Most of you just had digital right there. Let's see, you weren't in my digital class, were you? Up there. Were you in my digital class last semester? Yes, you were? Okay, well, I don't have my glasses on in here in the dark, so. I'm sorry, the guys are closer and I can see them. Two young ladies over there, I don't see you quite as well in the dark, but if I put my glasses on, there, yeah, okay, I do recognize one. I can't see the screen very well, my computer screen, so These are actually bifocals, but to see the screen, I got to keep doing it. It's better just take the glasses off. And trust me, everyone in this room will get older and we will have similar problems up there. My eyes started doing this when I was about 40 years old. So most of you have about another 20 years left of good eyesight. Although some people I know have good eyesight all the way until their 70s. And some of you are wearing glasses already, so it's all relative up there. And again, we will talk a little bit about BCD and ASCII and some of the floating points. We're going to get into a little bit more detail in this chapter that we'll actually use in the labs, because the 8086, I'll just kind of jump ahead, supports floating point numbers. The 8051 does not. So we'll spend a little bit of time talking about that there. Historical background. That's where we're going to get there. This is the part where most people want to fall asleep. So try to bear with me and stay awake as long as I can there. It is history up there. It tells us basically where we're at today and how we got there. So, and I am a firm believer that everything we look at in modern society has been greatly influenced by the microprocessor. It has changed more than you can imagine. And the reason I say that is I was born in the days before microprocessors, and I remember paper maps. I remember looking up phone numbers and phone books. You know, has anybody in this room ever seen a phone book? You've seen a phone book right there. They still print them. You know, I still see them from time to time. I don't know anybody that uses a phone book out there. So, so it is that there. Again, I'm going to kind of get up to the 8086, 88 family. I'm going to kind of stop there. I'm not going to go into and actually this book is a little older because it stops at the Core 2 processor. The i3, the i5, the i7 are the next generation that they're, as I said, my stomach is starting so while it's not essential, this is kind of a summary of my thoughts, all this history is not critical, but it does give you kind of a perspective of how fast this has changed. Because modern society, as we know it, has existed for roughly about, if we want to start that there, from an Islamic standpoint, about 1,500 years. You know, if you go back to recorded history, you have to go back to about maybe 3,000 years. Microprocessors have only been in existence for about 50 years. So, and if you look at the changes in society, the way that we live, the way we process information, the way we share data, the way that we live our lives, there's been more change in the last 50 years since the advent of the microprocessor than probably the previous 200 to 300 years. Right there. It's really changed the way, and it's accelerated, information, the way that we process information. I can walk around with 600 books in a Kindle right there because of microprocessors. You can pull out your cell phone and you can probably have, if you have a 32 gig memory card, 6 days of music on your cell phone, something like that, right there. So it's really changed, this fast-paced evolution, and it's changed life in many, many ways. Mechanical age, the idea of a computer system is not new. We could go back to the original abacus that the Chinese used about 2,500 years ago, were one of the very earliest ones. But the idea of calculating with a machine dates back to about 500 BC or BCE. This particular author uses BC. I don't know, is everybody familiar with the term CE and BCE? That's CE means comma era. In the Western world, they tend to use AD, but in Malaysia, you would not use AD because AD is a Latin term meaning the year of our Lord. So AD is not a biblical term here. but CE is Common Era, and BCE is, before Common Era. BC stands for before Christ. Right there. So just kind of a background. The terminology might look a little different because you probably don't see BC used very often here, do you? You've seen the term BC. Most of you know what it means, but there is a difference between the two terms. So the abacus, I just said the Chinese. I'm already made my first mistake was the Babylonians. So the Babylonians invented the abacus, that their mechanical calculator, that their strings of beads before math. I've seen people do some amazing things with abacus. And I'm not going to try to draw an abacus, but it's basically, I'll try to draw it. There, we'll see how it goes. It's that there, and you got a divider, and you got a bunch of that there, and you got beads that you move back and forth there to do calculations by hand. There, it was very effective for its time, very effective. But they're used by ancient priests to keep track of storehouses of grain. Still in use. There are still people that use abacuses today. Why, I don't know, but there's some people still get around on horses too, right? So, so the idea of coming up with some type of calculating machine did not happen 50 years ago. It happened really about 2,600 years ago. It's been a long time in the making. So, in 1642, I would not remember the date. You don't need to remember it. I do know that obviously Pascal invented the first calculator that was made of gears and wheels. Each gear contained 10 teeth, and it was a mechanical adding machine is what it was. And Pascal was a philosopher, mathematician. Back in the 17th century, they named a computer language after him called Pascal. Right there. So he is considered one of the early pioneers of computers right there. So it's been around a long time. When you move one complete revolution, the second gear advances up there. It worked very much like the odometer on your automobile or your motorcycle, as you count from 0 to 9. When it goes from 9 back to 0, the next wheel turns right there. So it's a way of there. So it's still used in, I didn't even read the notes there, where it's still used in the automobile odometer, but that's exactly the way it works right there. So when we look at right there, this is the basis of all mechanical calculators. Obviously, we don't use mechanical calculators anymore, but when I was growing up, we used to have mechanical adding machines where you push buttons and you pull the lever. You push buttons, you pull the, and you do plus minus to pull the lever. And it was the early calculators. It was all mechanical with wheels right there. And I wish I had one to show because they're big. I mean, they're and you would see them. A lot of the early cash registers used that. If you watch any of the old movies where you see the big cash registers, they're usually copper out there, and they would turn the wheel and the numbers would pop up right there. So these were based all on Pascal's original adding machine. And those were used all the way into the mid-1900s. I mean, actually they were still in use probably until the 1960s or 70s, these old style calculators, or cash registers. So as I just mentioned, Pascal was named after. Right there. He was a Frenchman. Right there with the name Blaise Pascal. You would assume that he was a Frenchman. Right there. So that was the first one. So the first geared mechanical machines to compute is the early 1800s. Right there. Early 1800s. That was when these old calculators and cash registers came around. The old right there. So they did exist. Again, we're talking 300 years ago. Babbage, Charles Babbage, was a pioneer of doing mechanical. There, he developed some early mechanical-based computers where they can be reprogrammed. Right there. And his assistant, Ada Byron, Countess of Lake Lovelace, which I have no interest in the fact that he was the Countess of Lovelace, but Ada is another name that pops up later on in honor. There's a computer language named after Ada right there. So some of these early names will pop up there. So in 1823, they built the first programmable that they're for the Navy. Now, you'll hear me mention from time to time the military aspects of how things were developed in the computer world and how much influence various military applications did. You can see that the first mechanical computer was done for the Royal Navy, the British Navy. So it wasn't the American Department of Defense that did it, it was the British Department of Defense. They wanted to come up with ways to navigate ships. Back in the 1800s, the British had probably the strongest navy in the world. Well, they didn't probably, they definitely did. And Malaysia is a good example of that, since they were one of the places that they came to and conquered up there. So they needed ways to navigate their ships, and so they had to come up with a programmable calculator of some type. And since the transistor and the IC wasn't invented, it was done with gears and wheels and things like that there. Fortunately, we don't have to look at the design of that. So he began his analytical machine, steam powered. They stored 1,000 20-digit decimal numbers. It was quite impressive for its time. I mean, if you think of the fact that it had to use a steam engine to drive this thing, that tells you how big this particular calculator was. And again, we're talking 1,000 numbers. That's 1K. What's your iPhone got in? Or your Galaxy Note or what? Galaxy phone? How much memory is in that? Right there. So it could do things that the first that they're used in the 1950s and 60s, punch cards came out as a way of programming. It said have to enter the numbers one by one, and punch cards were used by mechanical computers up there. I doubt if any of you have ever seen a punch card. When I took my first programming class back in the early 1980s, we actually still used punch cards. They were electronically read. They weren't run by a mechanical, but they would actually use little pins that would see where the holes were out there. And that's how you would write your programs. You on punch cards, you would feed them through a card reader out there. So soon the idea came from that they use punch cards. But this is kind of an interesting little note there, that the first punch cards were actually done to program weaving machines to make fabric in the UK. Back in the 1800s in France and England, that was where most of the fabrics were being weaved. And they had the automated weaving machines that they used punch cards in order to program the weaving machines, which was, again, one of the first steps of automated manufacturing out there. So, again, we're going back 300 plus years here. So, the loom that they're selected to integrate weaving patterns, punch cards program the loom. A loom is what they call the machine that makes fabric. I don't know how to make fabric. I don't know how to use a loom. But I've seen them. I've seen several of them that were used in the U.S. back in the 1800s by people out, in the prairie where they would get cotton and they would weave their own fabrics. So one of the things that their dream machinists of his day were enabled to create the parts, the machining capabilities were there to really get to work properly. I think my voice is starting to go too on top of everything else. So this machine required 50,000 parts. And it could not be done reliably. Today, making this weave would be a trivial matter with today's modern manufacturing techniques and machining. But at that time, they could not make it work. It worked in theory. It would work for half an hour, 30 minutes. It would break down. I watched a documentary on that probably 6 or 7 years ago. I think that, depending on what satellite or what cable TV provider you got, we have a channel called the History Channel, and this is not going to be up there. If we lose our screen again, got there where they went through the history of that there. So I'm not an expert on that, but up there. All right. The electrical age. That's the age we live in today. And we still don't have our projector. Okay, I'm not sure if it's. I don't think it's my adapter. I think it's the cable is going to this projector. Up there. So I will try not to move my computer. Up there. So the electric motor came out in the 1800s. Up there, the multiple electrically driven adding machines. Again, we've now taken the mechanical calculator designed by Pascal. We're now driving with an electric motor. So we can hit plus equal on the push button, and the motor would actually drive us and have to pull the crank. That was really about the only major difference between the old crank and that there is. These were around all the way through when I first started working. I graduated high school in 1974. That gives you an idea how old I am. That's there. And the standard mechanical adding machines were still around. The calculator really didn't come out until the mid-70s, late 70s, where you could actually afford to buy a pocket calculator. So prior to that, they were all mechanical adding machines. And they were based on Pascal's design still. So the first handheld calculator, I remember the Bomar Brain. I could not afford to buy one. They were about $400 to $500 USD in 1970 dollars. So if you would equate that with inflation, that would be roughly about 10,000 rands in today's money. And it added, subtracted, multiplied, and divided. It was a 4-function calculator. It was very, very expensive. And I'm very familiar with Bomar Brain because it was actually built in the city I lived in. Fort Wayne, Indiana was where Bomar had their plant. So I'm very familiar with it. It was actually designed and built in my, I wouldn't say my hometown, but where I spent the last 35 years of my life before I moved to Malaysia. So my entire adult life was pretty much, I call it home. Right there. So the Bomar Brain was the first calculator, electronic calculator. It appeared as early 70s. I'm thinking 72, 73 because I was still in high school when it came out. And I've seen pictures of them, and I actually saw one probably in a museum about 10 years later. They became museum pieces back there. They're very large too. So Monroe also came out with it. Monroe doesn't exist anymore. That company disappeared. And they also came up with a lot of Monroe was more of a cash register company than they were a calculator company. Okay, this is just a little bit more background. The Howarth punch card for storing data was still used all the way into the 1980s. And you guys still that around. He borrowed from the weaving machine that there. Again, there's just a lot of background that there. Developed a mechanical machine that counted, sorted, collected, collated information, stored it there. Again, driven by an electric motor. The calculating machine intrigued the U.S. government, and they decided to use it for the 1890 census. So, I'm going through and I'm talking about the history of computers being started as we know it in the 1950s, but you can see the concept had been developed over hundreds of years right there. It's just as technology has changed, the computers have gotten much more automated, much more faster, much more robust. But 1890 wasn't that long ago when you look at the history of man. Now, when you look at your history, 10 years ago was a long time ago. When I look at my history, 50 years ago was a long time ago. But when we look at the history of civilization, 1890 was like yesterday. Because we're going back 3,500 years for recorded history. Right there. The abacus was 2,500 years ago. So 1890 was like yesterday when we look at society. Right there. So again, the tabulating machine came around. I'm just sliding through these right there. Now the company that Howarth formed is still around today. So again, he formed a company called Tabulating Machine Company. Later, they changed their name to International Business Machines. And you would have lived under a rock since you were born not to have heard of IBM, right? I mean, IBM was a big player in the computer industry for probably a good 80 years. If you go, well, actually more than that, if you go back to, 1896, they kind of lost their dominance in the 1990s. So for at least 100 years, they were the dominant computer company in the world. Right there. So they've been around a long time. Right there. So punch cards that we call Howarth cards that we used to use that there. And about the same time that they also came out with paper tape that used the same type of concept. So mechanical electrical machines dominated until 1941. The first electronic calculating machine, Konrad Zuse, was a German, which ironically was about the start of World War II, or in the middle of World War II. So the Nazis here in World War II were very active in the computer development. That there. So his Z3 was probably designed for aircraft and missile design. Remember when I said military applications drove a lot of the computer industry? Right here, we mentioned earlier the British Navy. Now we're looking at the Germans here in World War II designing aircraft and missiles using his electromechanical computers. Right there. So, and actually, it's a relay, it used mechanical relays that had a clock speed of 5.33 hertz. Now, just imagine how slow that is by today's standards. 1 gigabyte or 1 gigahertz is 1 billion hertz. And this thing is operating at 5. It wasn't very quick. So, right there. And this is what it looked like. Right there. It would fill about a third of this room. I have not seen one of these personally, but right there. This just goes into more details up there. Okay, the first electronic computer placed in operation, that electronic computer, now this is one that is based on electronics and not mechanical, was developed by the British and the Americans, and it used a system invented by Alan Turing. Now, you still talk about Turing machines out there. It used vacuum tubes. The transistor had not been invented yet. Out there. And it was called the Colossus because it was freaking huge. It was big. Out there. And it was used to break codes. It was used in cryptology. Cryptology is the science of making, putting out codes that people can't read your messages unless they have the method of breaking the code at the other end. in a previous lifetime, when I was in the Air Force, I was assigned to a branch of the U.S. government called NSA, and our job was to intercept communications and try to crack codes. So I'm very familiar with what cryptology is and what this type of what this machine was used for. That's what I did for 4 years in the military. I didn't do anything exciting like fly planes. I sat in a room and listened to Russians over the radio and copied everything we said and then tried to crack the codes. That was one of the the code breakers at that time in the 70s. But this was one of the early machines that was designed to crack codes. Again, we're going back to the military applications of where computers really came into. I'm not a pro-military person. I am a veteran. I spent 9 years in the military. 4 years Air Force, and 5 years in the Army Reserve. So, and I come from a military family. So, both my parents were in the Air Force. My son was in the Marine Corps. My brother retired from the Marine Corps. So I'm fully aware of a lot of the military side of this. And I worked for the military complex for a while. So I've seen the military research put into the computer and the microprocessor world. And those of you that are anti-military, I understand that, but you wouldn't have a cell phone today if it wasn't for the military research. And again, the other thing where the military has been a big player is they put the satellites up used for GPS systems. That was all there. So the military has been there. So although the design allowed to break secret military codes generated by the, and I can't pronounce it, Ingina machine. This was a German computer that generated secret codes. It was a mechanical computer, and designed the Colossus was able to crack those codes, which made a big difference in the outcome of World War II. You intercept communications, they're encrypted, you could decrypt the information, and you knew what the enemy was going to do. It was part of the spy game at that time. And again, that was where a lot of the modern computer technology was part of the spy game. And it still is. So, and again, you can argue whether it's right or wrong to play the spy game, but its influence on computers cannot be ignored right there. So Colossus was not programmable. It did one thing only. It was a special purpose computer. All it did was crack codes. You couldn't reprogram it to solve a quadratic equation. All it did was you fed it codes generated by the German machine. It would then decrypt it and give it back out in plain text German. So the first general purpose was not developed by the military, it was developed by the University of Pennsylvania in 1946, after World War II. Now, truth be told, the military might have funded the research. They did a lot of that back then. So, the first electronic integrator calculator, the ENOC, had 17,000 vacuum tubes, 500 miles of wires, and weighed 30 tons. That was one of the very first real computers today. And it's probably the first real computer. It was completely programmable, but it was all vacuum tube based. And keep in mind that vacuum tubes, I doubt if anybody has seen a vacuum tube here, but they do wear out very quickly. And when you got 17,000 in the system, having a bad tube means that you get a lot of bad data from time to time. I remember vacuum tubes being on television since growing up. We'd have 20 vacuum tubes at the back of the TV, and whenever your TV broke, you would sit there and you'd take tape, and you'd number in each socket in each vacuum tube, and you'd carry them in a box to the local drugstore that had a tube tester. And you would try to find the bad tube. And that's how you fix your TV. Vacuum tubes were very common back then. Programmed by rewiring. There was no punch cards on this one. That there, it was reprogrammable, but you had to rewire the thing. When they say rewire, that doesn't mean going in there and soldering and unsoldering. Basically, you had a bunch of wires that you put through a push panel out there. So, it required frequent maintenance. And as I mentioned right there, that was a big problem with it. The tubes went bad quite frequently. So, again, life changed on this date forever in the electronics world. That when Bell Labs developed the first transistor, everything changed very quickly thereafter. We now have transistor radios that we can carry in our hand that would run off of batteries versus ones that ran off of vacuum tubes that you had to plug in and that were 3 feet high that sat in the corner of your room. Well, some of them were about a foot high. They got smaller, but the transistor changed everything in the electrical world, electronics world. Followed 10 years later by the invention of the IC, which is nothing more than a bunch of transistors put on a single piece of silicon. And the IC still is, today has been the driving force of most of the electronics today. Everything's done on ICs. But Texas Instruments is still a big company. They're still around. They have a facility in right off the MR2 up there, where they make IC. They don't make the ICs there, but they package them. There's packaging up there. I'm not going to get in. I might at some point go through the process of how an IC is made, but I'm not going to do it today. So the IC led to the development of digital integrated circuits in the 60s. Texas Instruments was the first, set up the standard for digital. When you took digital electronics last semester, most of you, we talked about 74XXX parts. Anything that starts with 74 was originally a Texas Instrument component part. That was their family of components. They don't necessarily make all of those. I remember as a student, I walked around with a little yellow book. I say yellow, it was about 2.5 inches thick. And it was the Texas Instruments IC guide, and it listed every 74XX part that Texas Instruments put out, along with the pinouts, the truth table, the data sheets, and all that stuff for that. It was a relatively, and that's what we would use in the lab every time we did a lab. If I wanted to use a 7404, I would look at the 7404 in the book and find the pinout. So Texas Instruments is still around today. Bell Labs is still around today, only they're now called AT&T. So a lot of these companies are still here today with us. We mentioned IBM was formed in 1896. Bell Labs actually was the telephone company in the U.S. Right there. So, and I remember seeing the symbol everywhere growing up of the Bell Telephone Company. And their drive was to come up with automated telephone switching systems up there. Matter of fact, my life might have been completely different, because when I graduated from college, I actually was given an offer by Bell Labs, and I didn't take it. I was working with Magnavox instead up there. So, but that was one of my companies I interviewed with was Bell Labs, just outside Chicago. So I'm familiar with them. But I'm also familiar with Texas Instruments. I've been to their facilities down in Houston. There. So these companies are still around today. So now this starts our course right here. This is everything leading up to right here, the first microprocessor, 1971. Again, ancient history by your standards. In 1971, I was a freshman in high school. So I was old enough to remember life before the microprocessor. We didn't have iPhones then. Matter of fact, the cordless phone wasn't even out yet. So, but the microprocessor was developed at Intel. 3 individuals, they were engineers out there. You know, these were big names at the time. These were there. They developed a chip called the 4004. Out there, they actually did this under contract for a Japanese company that wanted to build a microprocessor-based calculator. Out there. So, but they kept the design. They sold the chips to the company, but they kept the design in-house, and they further tweaked it and tweaked it and tweaked it and tweaked it, and they're still tweaking the original design. That's it. So it has a patent. We don't care about the patent number. But this device started the microprocessor revolution. So when we look at 1971, the first microprocessor is developed an entire new industry. We developed an entire technology. I call it an enabling technology. It enabled an entire series of new products to be developed around it. Right there. So when you look at certain new inventions or technologies, that if you invent something that does one thing, and that's the end of it, say such as an MP3 player, that is not an enabling technology. But the microprocessor clearly was an enabling technology. The transistor was an enabling technology. The IC was, but it was But the transistor, the microprocessor, would not have been developed if the IC had not been developed. And the transistor, or the microprocessor, is basically a large digital circuit placed on a single chip. But it is a reprogrammable by using software. So the big difference between the microprocessor and all the previous things that we talk about, the Babbage machine, the Turing machine, all these, the Abacus, those were not reprogrammable via software. You had to rewire them. You had to go there and you had to make physical changes with them. The processor now allowed us to come up with and write code for it to do certain things. So that's changed everything. Once the microprocessor came out, we had to come up with ways to program it. The microprocessor is a reprogrammable electronic digital it's a finite state machine. It goes through various states where it reads an instruction, it then goes to the next state, which gathers the information from various places. It does the addition and stores the information. It's a finite state machine that does things that they're driven by a clock. And we'll look at that in more detail later on. But we have to write software for that. The early practice of rewiring proved too cumbersome, so we came up with computer writing. So the microprocessor, the big difference is that we can write software for it versus rewiring. So the first machine language was constructed with ones and zeros, binary codes, and they all still work on ones and zeros. So as we get into assembly language and how it works, every instruction actually is then translated to ones and zeros for programming the finite state machine right there. But the first microprocessor, you actually had to program it with ones and zeros. It got a little bit easier when you could use hexadecimal. One of the early computer systems that I had, and they'll talk about it here later, was called an Altair 8800. I didn't have one when it first came out, but our university, someone donated a couple to us, and we were able to play with them later on. I spent some time with the Altair. And we actually wrote code by flipping switches to ones, zeros, load. Flip switches won't load, ones and zeros, load. And once we finished loading our program, we would tell it to run the program. We actually programmed it with ones and zeros. Very tedious process. Very tedious process. So we came up with time-consuming due to the sheer number of programs required. Again, I just mentioned that's the way we did it. They had 8 switches on it, a push button for load right there, and you would flip the switches and load. Flip the switches and load, and then you hit the run button, and it would go back to the beginning of your program. It would run your program right there. And it would show your output on a teletype. You know, your output would actually go to a teletype. That's what we had going to that thing. So you'll hear the term von Neumann later on. I'll talk about the difference between von Neumann and hardware architecture. First person to develop a system to accept instructions and store them in memory. So he came up with a way of storing the program in memory where it can be executed, which was used by the 4004. Computers are often called von Neumann machines in his honor. That later on you'll find that there's von Neumann machines and Harvard machines. They are different. That there is a competing that they're. Now Babbage actually came up with the concept before von Neumann, long before, but von Neumann's given the credit because he was the first one to actually apply it to modern computer systems. So once systems became available, assembly language was used to simplify. The Univoc was a vacuum tube-based computer, right there, and actually it was a transistor-based. We would use assembly language instead of using the binary code. And we're going to be learning some assembly language. I think we'll be using a lot of our early programs. We're looking at assembly language. All assembly language is another way of writing our code in something that resembles a Greek English type language. It's not very friendly at all. But you're going to learn a little bit of assembly language because it helps you understand how a processor works. If you go out and you do real microprocessor work, you probably don't use assembly language today. Just like in our basic digital class, you're forced to learn Karnaugh maps, right? But hardly anybody will use a Karnaugh map to do a design today. Same thing with assembly language. Hardly anybody's actually going to write a program all in assembly language. So it uses instructions that says add. A common assembly language instruction might be add A, comma, B, right there. So add whatever's in register A to whatever is in register B, and the result gets stored in A, right there. Or you might see something that says move A, B into A. Actually, this also makes things, when we get into the actual assembly language instructions, you'll see that they do it backwards. This actually goes this direction. Move into A, the contents of B is the way you would read that. But it allows you to write that instead of 011011100, which might be the machine code for move AB, right there. So assembly language is actually a one-to-one correlation to the machine codes, right there. When I first, and again, I keep referring back to ancient history, when I first learned how to program, we used assembly language, but we didn't have an assembler. We would write our code in assembly language, and then we would hand assemble it. My first microprocessor was the 8085, which I'll talk about in a few minutes, and we would have little cards that would list all the assembly language instructions in what their machine language, the ones and zeros. Actually, it wasn't ones and zeros, it was hex. We didn't use ones and zeros, we used hex. But this would be 6C, for example, would be the opcode for right there. That's not the opcode that it is. And by the way, these slides I will be putting up. They'll be on the e-learning site. They won't be on the Facebook site. But once I get caught up over the weekend, I'll make sure I put all the slides that I use up on the e-learning site. Has anybody been able? They changed the e-learning site. Has anybody logged on to it since they did the change? No. Okay. Well, I haven't yet either. So we'll see. Hopefully, it's a little bit more. I'm recording this. We won't say anything about reliability of the previous version. Okay. In place again. add, they're saying that this particular one is 47 is the opcode for the add up there. But whenever we look at assembly language instruction, there's always a binary opcode that goes along with that. But that was the first programming language, and that's what right there. Assembly language it's an aid to programming right there. The first high-level language, which I have never seen any code written in Flowmatic, but Grace Hopper is a very well-known name to the computer world. She was actually a Navy admiral, and I think she might have been the only female Navy admiral at the time in the 1950s. You know, the U.S. military up until the 70s or so was very sexist, and females didn't get promoted very readily to high ranks, but Grace Hopper was quite the genius when it came to computer technology at the time, and she was actually an admiral in the Navy, and she worked with a lot of the early systems up there. So, but Admiral Hopper was quite well known. Again, it goes back to that military tie to the computer world. So the Navy actually developed the first high-level programming language up there. So same year, Fortran came out from IBM. We mentioned that word IBM earlier, right? Up there. My first programming language was Fortran. Back when I was a young engineering student at Purdue, everybody was first required to take a course in Fortran up there. And Fortran was designed for solving engineering and mathematical equations problems up there. It stood for Formula Translator. So you would actually write, so it was not a general purpose language like BASIC is or some of the other languages, but it was actually designed more for engineering and scientific type work up there. So, and that's why all engineers had a background in Fortran up there. So I probably couldn't write a single line in Fortran today if I had to, because I have not used it I think the last time I used Fortran had been at least 25 years ago. It's been replaced with a lot easier languages to work with. Fortran was not a very easy language to work with. Fortran is still used by some, but not very many people. Most people have foregone Fortran. This book was written in 2009. That's about 7 years ago. That might not be true today. In the last 7 years, I think Fortran may have completely disappeared. So, Algo, I've never used Algo, but it's a similar language. Algo wasn't very popular. COBOL is a very interesting discussion. We won't talk much about COBOL. COBOL was written mainly for business applications, reports, a lot of insurance companies, banks, corporate companies that wanted to keep track of inventory, generate reports. It's a very wordy language. It's a very robust language for generating reports and those types of things. It's still around because a lot of those systems are still out there. And COBOL programmers, because there's so few left, actually make very high salaries out there. So COBOL is diminished, but it's still a big player. It's still around. COBOL is dying a very slow death. It will die eventually, but it's dying a very slow death. So the report RPG right there is one that I have used, and all it really does is it generates reports. It's been replaced essentially by Excel spreadsheets. I hate to say it, but spreadsheets have pretty much replaced them because very few people will sit down and write a program to generate a report today. And there's other software packages that will generate reports and do statistical analysis. SPSS is one. Trying to think of some other ones. I'm drawing a blank right there, but there's other software packages out there that generate reports much better than the RPG ever would do. So that one's pretty well died. COBOL, because it was so popular, still won't go away. But the early days, some other common programming languages have come and gone. BASIC is still around. Up there, back at my old campus, our first course is in Visual Basic, and our first course used to be, when I first started teaching at that campus, was Basic 8, IBM Basic. So we taught Basic as our first language. Our computer science department taught Pascal as our first language. Interesting, Pascal and Basic were never intended to be real programming languages. They were intended just to be teaching languages, but they found themselves in use in the mainstream. So they escaped the classroom the way Bright puts it up there. C# is a language developed by Microsoft. It's used for a lot of web design. C and C++ is the mainstay of microprocessor-based embedded systems, and that's what I use in the microcontroller course. That there, and it's the one I have the most experience with recently. That there, I do probably 75-80% of the work I've done in the microprocessor world, probably more like 90% in the last 15 years has all been in C or C++. Java is used a lot on web-based applications and things like that. You won't find Java used much in embedded systems. That there. Pascal is pretty much gone. That there. It's not used very much. Ada is a language that was actually developed by the Department of Defense in the U.S. and it looks a lot like Pascal actually. That there. So Ada was really used, and I've used Ada in the past because since the Department of Defense developed it, they required that anything done for them was done in Ada. So pretty much nobody outside the military sector used that Ada. It wasn't a very good language. It wasn't very friendly, but because the Department of Defense said that you had to use Ada, people used Ada. Right there. So BASIC is still used in many computer systems today. It's among the most common languages out there today. Still, you don't take BASIC in your program because you're engineers, but anybody that's going to do web design, you can easily write a basic, Visual Basic program and translate it to an HTML document and do computing over the web with BASIC. It's very popular with a lot of the web designers out there. It's also used by a lot of people for quick and dirty things. Visual Basic is probably taken over BASIC out there. Visual Basic is the Windows-based version, and you draw your program actually looks on that as a Windows, and it feels like any other Windows program. But it's the quick and dirty way to do it. It's very common and easy out there, and a lot of people just never bother to use anything but BASIC. Because, to be honest, using Visual C to get something done as Visual C is a pain in the neck in comparison to BASIC. Visual Basic is very quick and dirty. It's amazing how much you can do with it. It's a very powerful language. It's easy to use. And it's one that I encourage people to learn to use. Because if you go to work for an industry and you want to generate a program to do a certain calculation or generate a certain report, Visual Basic is so fast compared to other languages out there. So, I don't use it, but it doesn't work very well for embedded systems. It doesn't talk about hardware very well. But it's probably the best language for desktop computing applications. For quick and dirty. You wouldn't want to design something like Excel or Word with Visual Basic, something that complex. But the very quick and dirty things you can do very quickly, right there. So, again, right there, this slide, that particular point line, just going to emphasize what I just said, is probably 80% of the programs for personal computers are probably written in BASIC. It's by far the most common, and that's why our previous campus, that was our first language we taught was BASIC. And the reason was it instilled a lot of confidence in people to program. You know, one of the comments I hear is that everyone on this campus hates programming, and I think one of the reasons is your first language is C. C is not the easiest language to learn as a first language. BASIC is a much easier language to learn. So you know, if I was to redesign the curriculum, I would probably put a Visual Basic course in, then follow with a C course. Because that's what you know, I was part of the committee that designed the curriculum where I'm at, and that's what we did. That there. So again, when I say if I had my way, I would do what I did in the past. You know, I require a course in BASIC, and then follow it up with the more powerful engineering type language up there. So, with your Visual Basic, I just talked about Visual Basic a few minutes ago. That has made programming in the Windows environment much easier. It's very easy to write a Visual Basic program to do something. You simply draw the user interface and you just tell it how the text boxes interrelate, how the checkboxes work. It's a very easy language to write code, to develop Windows-based programs. Much easier than C or any other method here. This comment here that says it could supplement C++, Pascal is a scientific language, but it's doubtful. I'm going to say that it's probably wrong there on it's doubtful. I say it already, Pascal is pretty much gone. These slides are 2009, that there, Pascal is pretty much gone. C++ for short programs or special purpose is the only language I recommend. Again, I would not want to develop a very large, complex program on that there because it doesn't have the flexibilities of C or C++. It doesn't have the data structure, so it doesn't have something there. But it does do 90% of what people need to do. And strangely enough, you can mix languages in modern computer programs right there. You can write some functions in C, some functions in BASIC. So you can, that there. You're not in a course in, you're not taking computer engineering or computer science or information systems, so you're not learning to be desktop computer programmers, but if you would learn how to mix various languages and do that type of stuff there. C# is gaining headway and may actually replace. I don't think that is, I don't think is going to be true right there. I will disagree with the author on that. C# is a nice little language. It's not nearly as friendly as BASIC. It's not nearly as quick to put there. It doesn't have the hardware interfaces that C++ or C has. It doesn't have the interoperability that Java has, because Java will work on multiple systems, because Java is an interpreted language, where C is a compiled language right there. So, and we'll get into the difference between compiled languages and interpreted languages right there. And this is probably the most true statement right there, is that which becomes dominant remains in the future. In other words, what he's saying there is we don't know what's going to take off right there. We went through all these languages, and he says C# might replace this, Visual Basic could replace this. You know, he's guessing. In his last point there is he says, we don't know really. There may be a language we haven't seen yet that's going to do everything. So, okay, that their scientific primarily uses C++, up there, showed embedded systems right there. This here is 90% of the embedded world right there. If anything, this has probably moved to 80% right here. And my pen quit working there. I'm having all kinds of technology problems. This is probably 80%. Right there. Oh, now that part worked. This is probably more like 80%, and this is probably more like 10% now. Right there. Basic is probably gone, and Java's right there. Now, I should point out there are some new languages that he doesn't mention that are specific to the ARM, and I'm not going to get into that there, that actually probably replaces the basic in the Java for 10%. So there are some new languages that are not talked about right there. And right now, for whatever reason, I'm drawing a blank because I've written programs in them that they're nice little, that they're, but what they are, I just can't remember that they're. But if you're going to, say, for example, write for the ARM process, there's another language. It also uses C. It also uses assembler, but there's a couple other languages out there that are becoming popular. Almost complete control. This is the real. This is the key thing right here. These languages allow almost complete control over the programming environment of your system, especially C, C++. C++ is a language that is unique in the other languages. The reason is that C and C++ allow you direct access to the architecture of the processor. Pascal, BASIC, has to go through and you don't get access to port 0 or port 1 or port pin 0.2 or whatever. You get complete access to the hardware with C and C++. That's why 80% of embedded systems are using C, C++. 10% are using assembly language where timing is very critical and you have to have complete control right there. Assembly gives you 100% control because you talk to the processor directly in its language. C is translated from C to assembler by a compiler. You lose a little bit of that control right there. Now, as we go through and start doing some of the labs, what you'll see is if we write in C, it will generate an assembly language equivalent, which you could go and modify if you want to. But the other languages don't have that flexibility. So there's a reason why C is the top in programming at the embedded level. Other languages don't give you near the control. Okay. So again, this just emphasizes what I'm saying. I actually went through and scanned these slides beforehand, but I didn't memorize them up there. But that's why sometimes I make points before the slides up there. But C is replaces low level. You have access to the low level machine control. So you can write drivers, you can talk to the hardware directly with C and C++, where in the past you only could use assembly language for that. Still, many video games are written exclusively in assembly language. That's not so true today. Remember, these slides are 7 years old. Because these C compilers have gotten more efficient, much better. So the one thing about assembly language is that a well-experienced assembly language programmer will always write smaller and faster code than the compiler. But an inexperienced assembly language would probably always write worse code. So writing efficient code in assembly language takes years of experience. I will not call myself an experienced assembly language programmer today because I haven't done much in assembly language for real work in the last, I'll say, 10 years. I used to be a very experienced assembly language programmer, but it's like any other skill. You quit doing something for 10 years, you tend to forget how it's done. And the processors that I used to write assembly language for are not as common today. So So I would not feel comfortable jumping in there and writing a large bit of, large application assembly. I can write the ones that I'm going to assign you to the class, obviously, but I would not, design a jet engine controller, application in assembly. I would jump in and do it in C right there. So, okay. Assemblers can also interspeed or perform the interspeed of their. So, again, some newer parallel instructions found on the pen are only program one assembly language. That's not true either today. So, I'm going to, this I mentioned earlier before, I'm going to just kind of jump through these. Now, the microprocessor age, and how I have my own time. Well, I can see how long I've been talking. Oh, an hour, 10 minutes, okay. I'm near, I said I'm normally good for about an hour. I think now is a good time to stop at this point right there. We'll pick up right here because my voice is going. Do you have a comment? Did you have a question or you just raised your finger there? Okay, all right. Kind of a point I should have mentioned earlier, if I talk too fast, slow me down, okay? I'm trying to make a conscious effort to talk slower and with my head pounding a little bit in the background and my voice going away, I'm definitely talking slower. So with that said, one of the things I'm going to have to